Okay, so last time I was going over kind of generically the architecture for the different ways of organizing software, and we were looking at what Embed OS did. And so, just a few sort of closing items there before we move to the next lecture, next module. So, the embed, Arduino itself is provided on a variety of platforms, and the first generation was on kind of simpler microcontrollers, but in recent years it began to run on the so-called M-class ARM processors and comparable M4 and other such microcontrollers, which were substantively more powerful in terms of capabilities that they could provide, and in particular kind of true multi-threading and things like that. And ARM had created the Embed OS for it, which we went over it. So Arduino on these platforms is basically running as a thread on top of Embed OS, and in the process of doing it, they had to Arduino folks modified Embed a little bit. Part of it was that Arduino does not by default, Arduino does not, the hardware does not support the way Embed OS expects its platforms to boot up. So there are some changes and all associated with it, but those are kind of more engineering details. The main part is that Arduino essentially provides this abstraction that there is a setup function which is called, as you see out here. Let me see if I can enable. Anyway, so if you look at the code inside the purple box, you would see that that's kind of how Arduino in general sort of exposes itself to an application. So there is a setup, and then there is a infinite loop in which there is it calls the loop function that the user provides, and then it does and it continues to loop back. What Arduino does on top of Embed is that it basically modifies the Embed startup routine in order to run this. So essentially Arduino just becomes a thread inside Embed. So that's kind of the straightforward thing. Now the Arduino hardware itself therefore runs the Embed and then runs Arduino on top of it, and that naturally raises the question, could we just dump Arduino entirely and just run Embed? Unfortunately, it's not quite the case, because Embed requires kind of a different hardware abstraction. So in general, all Embed platforms come with a second processor, and the job of that second sort of puny little processor tends to be that it fetches a binary file. Well, firstly, it provides users with as if it's a USB drive, so it kind of provides that abstraction, and anytime a file is put out there, it basically loads it into the main processor, which is where Embed OS is running, and it loads it starting at address 0. Arduino, on the other hand, has its own bootloader already at address 0. And it doesn't have the second processor. So because of these details, because the boot process kind of just differs between the normal Embed platform and the way Arduino hardware traditionally has worked, so we can't really run Embed directly. But as I had mentioned at the very end of last lecture, one can access the Embed which is running under the hood, on top of which Arduino is running, at a C++ API level. So it's a little bit sort of kludgy, and you still have to run it through Arduino. But as this kind of code shows, in this particular case, at the very top you see that it says include embed.h, for example. So you kind of import the Embed OS. It's already there, so there's nothing deeper happening. It's just that you have to add it to your application, and then later on you kind of see, for example, we are able to run 2 threads. So if you look at the very bottom, you see that Blinker and Plotter are kind of 2 threads which are declared. We can think of them 2 tasks, and we start both of them, and we kind of have to call Embed APIs. So this is all C++ code, so the syntax and all has to do with that, but essentially you can still use the Embed OS. The code that I'm showing is from last fall's lecture, so there might have been some minor changes. Both Mbed itself and Arduino sort of keep evolving, but kind of that's the basic idea. So Arduino folks don't advertise that stuff directly. Of course, they want you to use Arduino, and that target market is kind of simple foreground, background type things. But there are, if you just kind of Google for it, you will see tons and tons of articles and all, including from the Arduino developers themselves. So actually, if you're willing to dispense with this whole view of what Mbed provides, if you're willing to dispense with it, it's an Mbed platform too. But this is not an Mbed platform in the sense that you cannot use it with the standard Mbed toolchains and Mbed Cloud Compiler and things like that. But you do have access to all those capabilities, basically. Okay, so that's one ecosystem, right? So Mbed is officially blessed by ARM, and lots of vendors kind of use it. There's a new OS which emerged over the past 2-3 years, and this is from the Linux Foundation, Apache Apache Foundation technically. Apache license and Linux Foundation. Anyway, long story short, this is an attempt to essentially create something which is the Linux equivalent for small processors. And so Zephyr had a lot more ambition, in the sense that it's not just for ARM processors, it's designed for a much broader array of platforms. They also pay a lot of attention to supporting a large number of devices and things like that to begin with. So I've sort of given a brief dump of what it does. It kind of at some level has a lot of features not all too dissimilar than Mbed, but this is far more powerful. Partly is far more ambitious. So it has multi-threading services. It lets you do inter-service. It has dynamic memory allocation. So does Mbed. You can have threads which synchronize. We kind of talked about in context of Mbed. There are similar things out here. So there are binary semaphores, which are like the mutex in Mbed, counting semaphores, which is just a plain semaphore in Mbed, and so on and so forth. You have ways of synchronizing, you're communicating between the threads, and power management. So a lot of these things that you expect. The nice thing is that it runs on a much broader array of platforms, including, as you see from the list out here, RISC-V and NEOS 2 and Tensilica. Tensilica is what the ESP32 devices used to use, for example. So there are a whole bunch of boards. So its main beauty in some senses is the scalability that it has. Getting started on it is a little somewhat harder, partly because Mbed has this cloud toolchain and all, and it has this the hardware was kind of co-designed with Mbed, so it's like really, like, as long as you have a computer which recognizes USB, external USB flash drives, then you need nothing else for Mbed. Whereas here, how you talk to the platform, how you download the eventually compiled firmware onto the platform, there is no standardization, mostly because Zephyr by design was aiming for a large number of different platforms. So in some platforms you may need a dongle, in some cases a serial USB to serial cable, in some cases, like the Mbed ones, indeed a flash drive, and so on and so forth. So it requires some more setup, and generally I've also found that at least setting it up, at least on my Mac, was considerably more effort than, let's say, Mbed was, but not something that I would say that someone let's say someone who's in an easy grad school or undergrad can't do it. But the target market certainly is somewhat different. Mbed, I think, can be used, Arduino plus Mbed, Arduino can be used by essentially non-engineers. Indeed, non-engineers use it. Arduino on top of Mbed, those platforms can effectively also be used by those. Whereas Zephyr, I don't just the installation process makes it clear that it's targeted more at engineers as opposed to those end users who don't wish to be engineers, just want to write their application. So that's kind of the different. So Zephyr OS, I guess as an OS itself, is also somewhat more capable, is how I would put it. In particular, I think its networking stack is a lot richer than what exists in Mbed. So for example, a lot of devices now that you find in your home automation and all, they use this whole networking standard called Thread, which Google sort of created and is now part of this whole ecosystem called Matter, which Amazon, Apple, Google, Qualcomm, a whole bunch of companies have sort of converged on. So Thread is kind of part of that. So you will see Thread being supported by Google Home, for example, or the equivalent products from Apple and Amazon. So Zephyr provides support for it. So if, let's say, there's a company, you're trying to create a product which exists in that ecosystem, Zephyr kind of makes sense. So I think going forward, and probably once I have ironed everything out, I would also kind of just switch to Zephyr as kind of the main thing. I think the writing on the wall is clear in the sense that it's a lot more capable thing. In your own, like if you want to, if you're looking for like which is the one OS I should list to make myself more attractive to companies and all, I would say at this point clearly it has to be Zephyr, because lots and lots of companies and all are kind of now building towards building on top of it. Even most of the MCU companies, they now essentially support it. Let me also actually just want to mention that I am unable to see the chat thing simultaneously. So if any of you have any question, I mean, chat blocks my slides, so that's why I like to keep it disabled. So if any of you have any questions, please just interrupt me orally. Okay, don't write on chat. Okay, so that's a bit about Zephyr. So in summary, kind of to recap this module, we kind of saw that between sort of today's last lectures material and a bit from the one before that, collectively we kind of saw that there's kind of the simple way of organizing things, which is just as a single task where effectively you poll for things. Then there is this foreground background where you kind of exploit the interrupt handlers as kind of a second thread, a higher priority thread if you may, one which always bumps off the main code. And this kind of stuff, arguably in some senses you don't even have a true OS of any sort. And then multitasking, which does require an OS simply because shifting from one thread to another thread requires context switch, and usually that kind of code is something that is trickier to write. It does need a scheduler, there are a lot of decision making, and this is where you get into the world of real something which can genuinely be called kind of an operating system. I've listed some of the software environments, and there are a few other things I just wanted to mention. So firstly, things like FreeRTOS, TinyOS, Contiki, Zephyr, Mbed, these are all operating systems somewhere along the spectrum. TinyOS is foreground background, for example. FreeRTOS is a multitasking operating system. Contiki is again foreground background. Contiki and TinyOS came out of people who did wireless networks of sensors, so they have very good stacks for wireless networking, but no one, I think at this point they're kind of largely obsolete, some of it simply because the wireless networking has become pretty stable. So what you get in Zephyr, for example, with the thread is NBLE, that's pretty good. FreeRTOS is used by Amazon for its AWS IoT, so their platform. So that's a large market, if you may. And then I already talked about Zephyr and Mbed, so that's kind of what exists. CircuitPython and MicroPython represent a couple of examples, and there are many others where people want to bring kind of essentially scripting like capabilities, right? We use kind of a dynamic scripting programming language of some form on the tinier devices. So both of these, as the name implies, they are kind of Python interpreters which exist on different platforms and supported by sort of companies. These I wouldn't say are kind of widely used in the sense of being any sort of standards, but they're pretty convenient. And if you are like CircuitPython is used quite a bit by platforms from Adafruit, for example. So these things provide a much more accessible introduction to embedded systems, much more dynamic. You kind of get a shell and you can kind of write to stuff, and also it's nice. Node-RED is an open source package from IBM, and it has a different goal of sorts. So it provides graphical interface which also work for distributed systems, in the sense that you can have pieces of code running on different platforms and all. And so Node-RED kind of gives you an abstraction where they give you a library of blocks, and then you connect them together, and then Node-RED kind of takes the burden of generating all the code. So let me see if I can. So this is a Node-RED website, and essentially you kind of create in a browser-based thing. You kind of create a diagram which represents a graph corresponding to your code. So essentially, you can think of each one of these blocks out here as kind of represent tasks and how the data are flowing. So those of you who are coming from more computing backgrounds, it's kind of like a data flow graph, and lots of people do use this thing. It's a pretty nice environment. Comes with a pretty robust tool chain and all, supported by a big company. We use it in my research group also. We have used it for a lot of projects and all. It's a pretty well done thing. Under the hood, these blocks kind of talk by sending messages to each other, and that's the abstraction that it supports. So Node-RED is it's kind of targeting a larger scale distributed systems where individual hardware nodes may be running, let's say, FreeRTOS or Mbed or whatnot, and Node-RED kind of layers on top of that. Okay, so I'm going to shift gears at this point and move to kind of next level up in this software story. So what we saw was how we think of software in terms of, let's say, modules which are somehow interacting with each other, right? I mean, so at that level, but we kind of left hanging this question that, okay, so we keep talking about sort of timing and the scheduling and all what goes on there, and the purpose of this module is to kind of one level deeper into what goes on in this thing and sort of what is involved, and in particular what makes it different from kind of normal operating systems where the primary goal tends to be kind of like throughput, in the sense that we just want to keep interactive users, as well as, if you are on a server, kind of keep the operators of the machine happy. Okay, there is no tight timing requirements, but when we come to embedded systems, that's one of the distinctive factors that we directly deal with issues of latency and all. So in general purpose computing, the way we deal with timing is in terms of, like, let's say we have soft promises about, like, we don't want the user to be unhappy, or if you are in a commercial setting, there might be things like we will do so many jobs per second. So there is this term in industry called service level agreement, which network providers and cloud service providers too, but they're always relatively soft, okay, and they're certainly not giving, even if there are constraints about latency, they're not very tight, and they're certainly not on every request that you will have. They will always be in terms of like, across a large number of tasks. This is what we will aim to do. So in embedded systems, in real-time systems, using that term generally, we have to kind of in particular deal with much more tighter timing constraints, timing requirements. So to the extent that in many settings, we want to design embedded systems where some of these properties can be guaranteed. That is, at the time you are designing, you want to be able to make claims that this piece of code, software that we have, when run on a particular piece of hardware with a particular operating system, is going to meet certain timing properties and all. And it used to be that a lot of this stuff basically used to be done in a kind of a hackish fashion. You design, you test, see if seems to be working, and you're happy with it. The problem is that as systems grew more complicated, that approach doesn't quite work. Something similar we went through in hardware side also, which is in hardware was simple, assuring that this chip, when we design and create on a particular semiconductor process, will achieve a certain clock rate, for example, used to be doable, relatively easy with the kind of things you learned perhaps in your first digital logic course. But as semiconductor processes became more complicated, as hardware designs became more complicated, it becomes a much harder job. So design tools, hard silicon compilers and VLSI design tools and their counterpart on the software side, essentially compilers, part of their job is to give you not simply to compile the code, but compile the code under constraints, so that assuredly there is a certain level of performance. Because if you don't, then at runtime, under some circumstances, the system may fail. And there are plenty of examples in sort of on the embedded system side where ad hoc strategies where kind of you tested and deployed, but then they failed, and often with catastrophic consequences, and that has given rise to approaches now where kind of when we deploy, there's a lot of prior assurance about our ability to meet it. So on this slide, I've sort of cited a couple of examples which actually spurred a lot of actions on creating more formally proven to meet timing requirements type approaches. So one was during, I'm pretty sure none of you were born or probably at the time, but 1991, this is the Gulf War, and there was an incident where America had this anti-missile system, and there was some incoming Iraqi missile, and these Patriot missiles would kind of shoot them down, and you see versions of these, modern versions of these anti-missile missile defenses present. So they basically fire another missile to kind of intercept an incoming missile. So as you can imagine, you have a rapidly moving target, and you're tracking it, and you have to chart out a intercept trajectory, and it has to intercept. And so these are, as you might imagine, by their very nature, very latency critical type things. And in this particular case, there was a tiny issue with how accounting of timing was being done in a for loop, and that was resulting in a tiny accumulation of extra delay every iteration of the loop. And since these systems essentially fundamentally at deep down, they have to measure time to chart out a intercept trajectory. So because of that timing error, the prediction was off, and therefore the anti-missile missile, the interceptor, would basically not intercept correctly. Okay, because even if your notion of time is wrong, but of course the 1 second in physical world is still 1 second in physical world, so it would getting distances wrong as a result. And this had in one particular case, it had catastrophic consequence that the missile ended up killing a lot of soldiers. There was on a different side, there was another issue. So we talked about semaphores last time. So you can now imagine that if you have two tasks which are sharing a resource, let's say sharing a radio, sharing some data structure, and now you want to promise that come what may, both the tasks are going to meet their deadlines. It becomes a tricky thing, because to be able to say that one task will meet its deadline, you have to be able to say something about what happens when the other task needs the resource, is locking your task out, which therefore has to wait. And again, the theory behind it, how to reason about it, didn't used to be known until mid-90s or so. And there were incidences where there were situations under which, under rare circumstances, the system may fail if you don't account for it properly. So anyway, Mars Pathfinder, this was one of NASA's mission to Mars, where they had sent a robot, a roving robot on the Mars surface, and which would collect samples and all, and for whatever reason it would reboot very frequently, and the problem turned out to be on the part of the code which was designed to handle this. And the thing is that the theory, the way to reason, the mathematical way of reasoning about it and coping with it had just about then emerged. So these systems were still being designed without that in mind. So, and there are lots of other examples. I mean, there are more modern versions where failures of sensors actually, I mean, how not to design system was also exhibited. I think two more recent incidents. One was the whole Boeing Max 800 one, which is fairly recent, and also one of the Airbus crashes, again kind of owed back to it. And these are all sounds from aviation, but similar things have happened in other domains. I think Toyota, which had the braking issue, and that again was traced back to a firmware issue. So these challenges exist, which is you are deploying these systems where time plays a critical role, and components fail, and you are still trying to provide kind of performance which you can make some assurances about. This is Space Shuttle, the very first flight of Space Shuttle, where transient CPU overload caused problems. And actually, the interesting thing is, in many of these cases, including the Pathfinder one here and this one, they are subsequently, once they identify the bug, they are also able to calculate, what was the probability. And lo and behold, in all these cases, the probability of that happening is pretty low. But Murphy's law always comes in our way, that at runtime you kind of face these challenges. So in this particular case, again, it had to do with some redundant processor going out of synchronization. This is the Patriot missile slide. So I've already described to you the main issue out here was that the real-time clock which was maintaining the time, it was accumulating an error of 57 microsecond every minute. Sounds very tiny, but part of the consequence was that the longer the system was running after reboot, the more error would build up. And in this particular case, when the accident happened, the system had been operational for quite some time, 100 hours or so, and usually the system was much flakier and it would reboot on its own or whatever. It had to be rebooted much more frequently. So in this case, that error translated into 343 millisecond of timing error, which resulted in a prediction error of 687 meters. Okay, so long story short, even tiny errors of time accumulated can lead to lots of errors in other aspects of your system. Okay, so what all of this leads to is that one has to be able to make some confident assertions about timing behaviors. But before that, one of the things then you also have to say is that how do I think about the timing constraints? What kind of timing constraints should should exist, right? And if you kind of think about it again, in our normal software, not real-time software, we often do indirectly deal with time, but we don't worry about what is happening. So for example, let's take our normal, if you're writing code in Python or C++ just for normal purpose, it's not unusual that we would say things like sleep for whatever 1 second or something like that, right? Or wake at a certain time. We never really think about how much error we are willing to tolerate, because the applications we deal with are not particularly tight in their timing requirement, right? I mean, usually we are using these timing in a pretty soft manner. So we never even worry about it, right? I mean, when we tell our Linux system sleep for 1 second, do we really care that if it is 1.1 second or 0.9 second? Most of the time that's not really an issue, because we're just dealing it in a softer manner. But when you're dealing in the real time systems, you have to be a lot more precise about these things. So for our purposes, then the problem that we're going to look at is scheduling under timing constraints, and there are many variants of this problem that exist. First thing is, do you know beforehand what are the set of tasks now, or is it the case that new tasks arrive and depart in your system? Okay, so obviously the first problem is a lot easier to reason about, right? That if I know at design time that I have these tasks in my system, then it's one, I can reason about these things at design time. On the other hand, if a new task may enter into my system while the system is running or depart the system, then it's kind of different. Then at runtime, I have to check that with the new task, would the system still be operational? Then another one is, am I dealing with a single processor, or am I dealing with a collection of processors which are networked or sharing memory? And as you again might imagine, the former version is obviously a lot easier. Then what kind of timing behaviors we are dealing with? So I'll give a couple of examples. One case could be that I would say, I have a task which comes every time delta, and I just want you to make sure that you finish it before the next copy of that task arrives. Okay, so it just arrives every delta, and that is how in a lot of signal processing in such systems we deal with it when they're running on a single dedicated processor, right? I mean, let's say I have sensor data coming in, feeds into some processor, and then that's all we care about. On the other hand, there might be settings where there is no such periodicity, I don't know, but an asynchronous event may come indicating, let's say, a collision is imminent. And as soon as I get that, I have to make sure that I take some action within a certain time delta. Very, as you can imagine, very different requirements, very different settings out here. If we have multiple tasks, then there are other issues which come in. Is it, do the tasks carry some state? Do they have some memory, so that, or is it that each copy of the task independent? So like, for example, if I'm getting a sequence of sensor data, if I'm processing sensor data sample number I, do I need to remember something from the previous sample, right? So that would be the state, versus each sample is independent and it doesn't need to know anything about what happened before. Stateless cases are easier to optimize for. If I have tasks, let's say one handling a camera and another handling a radar, are they dependent on each other somehow? So maybe they are using the same GPU, for example, or some shared resource or same data structure. Can I bump off the task in the middle? Is the OS allowed to do that? So all these kind of things which make things different. Let's start with, how do we specify timing constraints? And there's nothing sort of deep about it, but kind of just wanted to lay out what the taxonomy is, because normally we don't think about these, right? In general purpose computing, like I said earlier, it's usually we think about timing in very, very general terms in terms of its throughput and such. So if you think about any system, there are two types of timing constraints that one has to consider. There are timing constraints which are which are something about the performance of the system, right? Which are placing some demands on the system, and then there are timing constraints which really are making a statement about the environment, because environment you can think of that timing constraints that we design for is kind of like a contract. The system, we are going to design the system, but there is the other party also, namely the physical world or human world, and both we are going to design our system with certain expectation from the physical world. So there are so the former category are performance constraints. These are constraints on the performance of the system, and then the latter category are behavior constraints, which make which are making in some sense an expectation or a demand on the surrounding environment. And if the surrounding environment doesn't keep up its side of the bargain, then our system will fail. Of course, the big part out here is that are those expectation from the surrounding environment, are they reasonable and correct? Because you don't want to design a system where there would be unreasonable expectation from the user or the surrounding environment. And I think a good case in point is what happened in the Boeing 737 MAX 800 example, where apparently kind of the to recover would have required a level of training and strength that most pilots didn't have. So that was an example of kind of a bad assumption about the pilots. And likewise, the system was designed with a single sensor, so when the sensor failed, apparently there was no real way for the system to tell what was happening, right? So there was no other baseline to check with. So so even behavioral constraints one has to be careful about. Within these, you can, sticking to timing, one can say that timing requirements, timing constraints can fall into three categories. Sometimes we have constraints which are about maximum time. Okay, so for example, we may make a statement about that between two events, no more than this time should elapse. And likewise, you can imagine a minimum constraint where we would say event 2 must occur at least time t after event 1. And then finally, events are often not simply at a point in time, but they are an interval, or they are a duration themselves. And we may have a statement like this event must be of a certain duration, okay, not just be instantaneous. So let's look at some examples of this, how they play up, and then at some level, when you're designing the system, you're going to think in terms of these, but deep down, everything has to then translate into something that the lower level software kind of understands, okay? And in case of operating systems, it basically boils down to latency. So latency for a task, from a point a task starts to the point it must finish. So maximum timing constraints can come in 4 varieties, and likewise minimum timing constraint. So if you think of the system and the environment, then you can say that the input to the system from the environment is like a stimulus to the system, and the output of the system which goes to the environment is the response. So input is stimulus, output is response, and now you can have maximum timing constraints which occur between one input, one output, a pair of input, a pair of output, or successive things on the same input. So let's look at them. Stimulus thing, it's basically saying that occurrences of two stimuli to the system must not exceed a certain time. So like for example, we may say the second, let's say we are designing a telephone system, okay, or some sort of a keypad, and we say second digit must be pressed or dialed no later than 20 seconds after first digit. Okay, so old days telephone systems was kind of a running example of system which had hard real-time constraints, and also a lot of these protocols were designed in telephone systems with human user in mind. So kind of the idea is you pick up the phone, you press a digit, the phone system would then say, if you don't press the second digit within 20 seconds, I'm going to assume that you're no more there. Okay, and right, I mean, so that's kind of a setting out here that the stimulus combination is really placing expectation on the environment, that the environment would press no later than 20 seconds, whatever the next digit after the preceding digit, and if it doesn't, then the system designer can ignore that, for example, or is not bound by this. So this is A is clearly kind of a requirement or an expectation on the environment. SR, a maximum time is allowed between the arrival of a stimulus and the system's response. So for example, after I pick up the phone, or nowadays press something, you shall receive a dial tone no later than 2 seconds after lifting the phone receiver. Now I guess nowadays with a smartphone the concept of dial tone has gone, but if you still have a landline phone, you know, like you pick it up and a dial tone has to come, right? I mean, so that response time, this is something where the system, in this case the telephone switch, right, the telephone company, so after I pick up the phone, they're giving us a performance promise that they will respond to our action of picking the phone no later than 2 seconds. So deep down in the software layer, you might imagine that when we pick up the phone, a new task was maybe created and it would generate the dial tone. So there is some implied latency that kind of the system has to honor. So this is the second case, is a requirement on the system, and you can see how it might translate into a latency requirement on the underlying system. RS is response to stimulus. So a maximum time is allowed from the point system gave its response to when the next stimulus comes. And again, in this case, as you might imagine, this is really making a statement about what we expect the world or the user to behave. So in this case, the example being, after receiving the dial tone, we expect that the user will press the digit within 30 seconds. So again, if you are designing the software for the telephone system, you would say, if I after receiving the phone turning on and I generated the dial tone, I'm not going to wait more than 30 seconds. If the user doesn't press the digit, then I'll assume no more there. And I think in most systems, again, landline smartphones don't have this concept of dial tone, but in landlines, if you don't do it, then a weird rapid tone starts coming after some time, right? So the system says, I've given up. And so that's again on the user. And then finally, response is when the system is supposed to generate two responses, two events, and this is a constraint we are specifying on the distance between those. So for example, after a connection is made, the caller will receive a ringback tone no more than half a second after the callee had received the ringtone. So this, in this case, is a distributed system, and when so there are two things which are happening, right? When a connection is made, the receiver, the entity you are calling, namely the callee, its phone will ring, and also the caller is informed that there is a ringtone going there, right? I mean, when the phone rings, so you kind of start hearing, and the other party's phone rings, and it's basically making a statement about the latency between those, because again, you don't want a situation where caller starts hearing the ring, but the callee's phone doesn't ring, or vice versa, right? Again, would be bad for user perception purposes. So in this case, two events at two different points, there is a certain latency requirement out there. You can imagine other versions of this. Let's say I'm going to be applying brakes to two wheels in a car synchronously. I have to make sure, so there might be something about that, the braking events on the two wheels should be no more than a certain time apart, because if they are not, then one wheel will have the brake applied, not the other one, and maybe the vehicle will sort of have a weird rotation action or something, right? So there is a simultaneity requirement that exists in many systems, and this would state that. Let's see, I see something on chat, so okay. So firstly, again, one request, please interrupt me orally, because unfortunately Zoom doesn't allow me to deal with the chat window very easily. So a response from another device is a stimulus or another. So I guess I'll give you kind of an answer to it, which you may not find satisfactory, which is it depends upon what your system is, right? I mean, so if I'm part of a distributed system and I'm responsible for designing one node in it, and the other node, or to use your language, the other device, to me that is part of the environment. So in distributed systems, a lot of effort goes on in defining the expectations and these boundaries. On the other hand, if you were the one who was designing that protocol, right, I mean, what the distributed system, then for you, that multi-node system is a system, and now you're going to reason about what is a reasonable value. And a lot of time, the standard setting bodies and all in these systems, when they're partitioning things, there's a lot of horse trading goes on, because what may happen is, I'm going to take computer networks as an example. You are a Cisco, you are in the business of designing the switches in the network, versus you are an Apple and you are designing the devices, the edge. And both sides want to keep they have a shared interest. They want to create a new distributed system, a new way of communication, which has good performance, but both parties want to keep their life simple, right? So Apple would try to veer the standard towards something where its job is easier, and Cisco in the other way. I'm kind of picking these companies just randomly, so don't read too much into it. So to answer your question, so whatever, for a company, the system is the box it is making, but if you are so REST is the environment, and the standards will define what the constraints are. So stimulus response would be in terms of those. If on the other hand you are playing the role of kind of thinking about the whole big distributed system, then everything is still internal and your users are your environment. So hopefully that answers you. But yeah, good question, because what is environment versus what is internal to my system depends on the circumstances. I like to often sort of think along the following lines, that whatever I'm designing, whatever my company is doing, or whatever my group is doing, is a system to me, but and everything is external world, and so you kind of work from that level. And also over time, sort of as we integrate more and more things onto a single package, again our notion of what the environment is changes, right? Because we are able to pack more stuff. So yeah, what the environment is really sort of whatever interface contract you're trying to meet. The same thing with minimum timing. I'm going to skip that. It kind of follows the same track, and in context of any system, you can kind of reason about minimum examples, or maybe I'll pick one. Let's look at B, SR combination. A minimum time is required between the arrival of a stimulus and a system's response. This is kind of an interesting one. You'll say, why do we want to slow the system down? Right? I mean, in some sense, it's saying system should not do something sooner than something, and kind of in systems where your user interaction has some complicated things, you may face this issue. So like, for example, oftentimes you have these buttons on devices where they would have these kind of behaviors. Press the button for more than few seconds, but no more than so many seconds to reset the thing, right? I mean, like I was dealing with my Wi-Fi access point over the weekend, and it had this weird thing: press the reset button for at least 5 seconds to reset it, but don't press it for more than 20 seconds, because then it goes into a FTP based remote boot up mode. Okay, so sometimes timing has these kind of requirements. In the phone system, which is what is listed out here, after the caller had dialed 0, the system shall wait 15 seconds before dialing. And kind of the idea is that sometimes in older phone systems, when you press 0, you want it to actually it involves some sort of operator assistant, basically operator assistant. So many systems you'll see kind of this kind of a minimum requirement kicking in. Usually in systems where we are making use of time to encode some complicated behaviors, you will find very commonly such things. There might be far more complicated timing constraints also, right? There may be more things that involve multiple sequences and all. So, or multiple events, not just between pairs of events. So there are some examples out here. Like for example, not only are we saying 2 digits must be dialed, like 2 successive digits must be dialed no more than some time apart, but maybe we may have something about an overall thing also. The caller should dial 7 digits in 30 seconds or less. Okay, so you often see kind of requirement like this, that certain number of events must happen in a time duration. It's kind of like what a game of chess. You must make your moves in whatever 1 hour or something like that. There might be other constraints like, so let's look at the second one. To get back to the operator, press the button for at least 15 seconds. To get the dial tone, press the button for more than 30 seconds. So this is very similar to that Wi-Fi access point thing that I was saying. So anyway, so complicated requirements can come up, and part of the challenge is how do you express these things, right? There is a whole rich literature that exists dealing with these things. Generally speaking, I'm not covering that, but basically kind of events are nodes in a graph, and constraints are edges in the graph. And if you have constraints which involve more than one event, then you have kind of more complicated edge structures like hyper edges and hyper nodes to kind of capture that. So the rich literature, this is an area which sort of has received lots and lots of attentions over a matter of decades. So it's nothing sort of terribly new. If you will find people attempting to deal with these issues even back in 70s and 80s, because as you can imagine from my examples, like telephone system was one of humanity's first computerized distributed system. So a lot of work happened then. It had real-time requirements, it had requirements of resilience to attacks and things like that, and also a lot of work happened. And I think now and train system was another one which was like that, signaling systems in train. So a lot of underlying theory and all began to be developed sort of quite some time ago. And as we I mean nowadays I think we are more in business of just sort of like using them, how to express and reason about these. There are still people who work in it, but not the primary focus. You can kind of put it under, there are tools available, mathematical tools available for you to exploit. So there are things like Petri nets and all, which are theoretical tools that were developed quite some time ago. For our purposes, one of the things to consider is that timing constraints, these things need to be expressed somehow, right? We need they need to be expressed by designers so that implementers can know what the specification is, but more crucially, the implementers need to express them in the code they write so that the OS or the hardware can honor them. So for our purposes, you can abstractly say that how do we express these constraints in our languages and operating systems. And at some level, even the most general normal code may have some timing things, right? I mean, when you tell the system sleep for 5 seconds, you're really asking. Actually, I've never bothered to look at it, but like if I tell Linux sleep for 5 seconds, it would be interesting to know what exactly is Linux supposed to promise. Am I asking it sleep for at least 5 seconds, sleep for 5 seconds plus minus epsilons? Like what exactly is being promised? I don't know, but we certainly can't be saying sleep for exactly 5 seconds to write down to like precisely, because we can't, the system can't do it that way. But when our code says sleep 5 seconds, there is clearly is something which is making a statement about time. There are what other things we can ask the system? What is the current time, right? Again, we can say like in Python there is now, right? And again, there is something implied out there that what is the time now to certain accuracy, which we don't necessarily specify. Sometimes you may also have wake up at a particular time, or if you have used anyone knows what cron system in operating systems is? Anyone used it ever? Cron tab. So if you're using Linux or Unix systems, there is an under the hood kind of thing where you can have jobs which are scheduled to run at specific times. So like you can say every Tuesday or whatever, every alternate Tuesday at 11 a.m. do this, and then you can specify a command, and then the system will do it. So it's often used for background cleaning up tasks and all, like file backups and all, but you can imagine doing other things. So in operating systems, you do have this ability of scheduling things to happen at a certain absolute time. So that exists. If you are in systems like Arduino and all, they have timers and you can do things. Okay, so going back out here to the slide, I can measure elapsed time in Python. How would you do that in Python? Anyone? How will you measure how much time a particular piece of code took? Just speak up, anyone? That's easy. No.
The time library, right?
Yeah, but tell me precise function, like how do you measure time?
There's a function I think called time in the time library, and you maybe stores like the start time when you start like running up the code, and then at the end you measure the time and subtract the two.
Okay, so kind of, yeah. I mean, there's a time library. There's a function in there which tells you what is the time now. So essentially, one way to do this thing is that you can say t1 equal to now, run your code, t2 equal to now, and then do t2 minus t1, right? So something like that. So yeah, along the lines of what you're describing. There is, if I'm trying to measure how much time a particular function takes, let's say I've written a function to compute FFT, is what else should I worry about if I'm trying to characterize the delay of this function? Like, can I simply say, okay, my strategy, right? T1 equal to now, on let's say 2 random inputs or whatever, on a random input, I do call my function t2 equal to now, t2 minus t1, and I report that this is how fast my function is. Do you think that's okay?
Have some delay associated with those function calls too.
No, but that's what I'm trying to measure, right? I mean, okay, so delay associated with what? The call to
the time library function.
Call to the time library, yeah, but those are, let's say, those are optimized, right? I mean, actually, they tend to be pretty optimized. Anyone else? Like, what else? If you are measuring some phenomenon, in this particular case, how long the function takes to execute. What all things can affect a measurement on a processor where you're running this, right? So we talked about it, right? I mean, if you're running a piece of code, what may happen in the background? Something else can come, right? So your T2 minus T1 may not be reflective of just your runtime. So that's one thing. So you'll have to make sure that you're measuring not the wall clock time, but the CPU time, right? Because if the operating system bumped your function off while it was in the midst of execution, then that's not what you want, right? So one of the things you have to take care is that T2 and T1 are not representing wall clock time, but system time, right? The system time that or the CPU time that was given to your process. But right, so in Unix, time is maintained in many different ways, but one of the ways it maintains time is how much time your process has been running on the CPU. And so every time your process is bumped off, wall clock time is still advancing, but your process's time is not advancing. Okay, so at the very least, you'll have to make sure that instead of using wall clock time, you are using the time corresponding to how much time your process has used. Now, not every operating system provides it. So one of the things you may have to do is to do averaging, right? I mean, okay, any given run can be perturbed, but maybe I'm going to do 1,000,000 runs. Other variations when you're measuring elapsed time may come from, maybe there is data dependency. Maybe my code runs faster for some data values and slower for others. There may be cache effects, right? When maybe the first iteration may be different because the cache may not have the data that I need, but once my code is sitting in the instruction cache, then things might be would be more rapid, right? The instruction is no longer being fetched from the DRAM, or worse yet, from the virtual memory in the hard drive. So measuring elapsed time when you are doing it for code profiling and all, one has to be pretty careful. And you would see that generally these systems, what they do is, like when you are estimating how fast my code runs, you do it by averaging over many cycles, and you discard initial cycles. Okay, this is just a side note. Back out here, I mean, measuring elapsed time is one thing that we need to do. Delaying a process, right? So sometimes I did something and now I have to wait for a certain amount of time before doing the next thing. This is kind of like the minimum constraint that we talked about. So right, so I have taken some action, and the next action I have to do only after some time has elapsed. What would you use out here? The slide show suggests something. You sleep, right? You put the process to sleep. That's one way. That's the best way of doing things. If the operating system doesn't provide you with any way of sleeping, then you are going to create your own sleep by doing nothing. So the most common way of doing nothing is I'll measure very carefully how much time an iteration of a for loop takes, and then I'll say for I equal to k down to 0, whatever, just iterate, and that k is selected by careful calibration. Of course, the awful part with this approach is OS has no way of knowing that you are actually you are just killing time. So that's why you should look for sleep function to kind of do that. So delaying process is another thing that we want to do. Timeouts. So timeouts basically is I made a request to some service, some operating system service, some remote service, right? And but that service is going to take some time, but there is also a possibility that something bad happened and I never get back the answer. So I want to specify a max timeout. I'll say read from the radio, but don't wait for more than 1 second. Okay. So in this case, or if you're writing any like so let's say there's a read function which takes the radio ID, but now there will be another parameter somehow, a timeout. Don't wait for longer than that. So this brings to this notion that in systems you will find whenever you are doing some sort of, let's say, interaction with an IO, then you have a blocking IO where you say, read this thing and I'm going to wait until you supply that to me. Now, as you might imagine, that's a pretty tricky way of doing. You better be assured that you will get a response, because otherwise there is a chance that you may wait forever. So that's called a blocking IO. And a lot of times we just use blocking IO because we just make an assumption rest of the system is pretty sane and it's going to work, right? Like, for example, sometimes I may say, once I have opened a file to read or write, then we pretty much assume that the file system on our local machine is, if I say read a byte or write a byte, it will return immediately. It won't be that reading a byte will take a undeterministically long time. I mean, it's possible when I say read a byte, it will return immediately saying there are no more bytes to read. That's fine. I get a response immediately. And if there's a byte, it will give it to me in reasonably fast time so that I don't worry about the wait. But what imagine now what happens if you're trying to read from a serial port or something where the bytes may be arriving leisurely, right? I mean, now you say read and you may have to wait because it's still an open file. It has not reached end of stream. So this is where in these kind of settings you may want to specify a timeout saying, okay, read, but just in the event something bad has happened at the hardware level, I'm going to specify a timeout. Okay, that's one way to do it. The other way to do it is repeatedly check with the serial port. Do you have something for me to read? Do you have something for me to read? So you do a non-blocking IO, right? As in you just poll the thing. So anyway, timeouts are important. There are other ways of doing it, but potentially deadlines. So that's probably a lot of these preceding things can be morphed into some sort of a deadline. We are basically say run this function but finish it before a deadline. Okay, and that's probably the most common thing that distinguishes real-time operating systems from others, that there is a task. You can think of a task as a function which needs to be completed, okay? And deadline basically is I'm telling the OS, run this task, or run this function on this input and generate the result, and make sure you don't take more than this time, right? Or more precisely, I want it to finish 10 seconds from now, right? I mean, so I basically give a deadline relative to when I gave it the request. Needless to say, there is a minimum time that the task will take depending upon the CPU I am running on and what the task is, right? I mean, you can't finish faster than the computation that exists in that task. But if I tell the operating system you can take more time, so let's say I've tell the fund do this FFT, and let's say FFT, if it had the CPU fully on that data, would have taken 1 second, but I tell the CPU from now do no more than 5 seconds. So now it has 4 seconds of slack, and it can make use of that to run other things, accumulate other stuff. So deadline is in reference to that. So these are some common examples, and you can imagine some others other time abstractions that you would see. These 4 are all kind of independent of absolute time, but some languages and all some operating systems provide have a knowledge of absolute time, as in world time, and make references to that, right? I mean, so like do it like the cron example I was giving, do this task at 5 p.m. every first Tuesday of the month, for example, right? Usually you won't find these things in programming languages. or OS directly, but you will find some services or applications that in turn provide some capability like this. Okay, so what all of this boils down to then is that so this is kind of still at a higher level. Deep down, the simplest abstraction that operating systems support is this notion of tasks, real-time task, which is specifically really this final point, tasks with deadlines. So the idea being that there are tasks, and from the point the task becomes ready or arrives, if you may, I want it to finish by a certain deadline. So you can think of it as there is a set of tasks which, let's say, represent different functions my system does, right? Maybe reading information from a bunch of sensors, there could be the reader task, then some other task maybe about processing them, and then some other maybe computing, combining their value into a single set of values, and then another could be perhaps sending them over. So oftentimes we think of our system in terms of, like, we break down the system into these tasks, and a simplifying assumption often we make in a very simple setting could be that they are independent. There's nothing, they don't share anything. Okay, these tasks don't talk to each other in any manner. They don't send messages to each other. They don't have any shared mutex, semaphore, nothing. Okay, they don't interact with each other. Second thing, again, simplifying assumption, these tasks are periodic, but they may have different periods. So essentially you can think of a task as arriving every period, and then that's a new copy of the task. Sometimes people refer to that as a new instance of the task. So for example, if I have a task reading a sensor, then every time the sensor produces a sample, which is commonly done in a periodic manner, then every time that sensor data is available, my task runs. Very commonly it could be that there may be a timer associated with that sample period. So every time the timer fires, I have a sampling task runs, and that sampling task would read the sensor and then do something with that data. So in this case, T1, T2 through Tn represent the periods corresponding to tau 1 through tau n, which are the tasks. So another way of saying is that the arrival rate of task tau I, is 1 over Ti. Okay. Then the third bullet is so the system starts up, and then after a while the first copy of task 1 will come, and first copy of task 2, and on. And in general, the first copy of ith task and first copy of jth task may not arrive at the same time or even in the same order across different runs of the system, because these tasks are potentially coming from outside. They may be coming from the network and all. So you can think of, after the system started, let's call that time to be t equal to 0, then the first copy of ith task arrives sometime after the system started, and let's call that time to be r sub I. So r you can think of as the time or the phase of the first request of the ith task. So r sub I is the arrival time of the first instance of tau I. Now if you think about it, if we knew r1 through rn, as in these were given to you as fixed values, then everything about the system is known when it starts up, right? Because then I know the first, after if I look at task number I, then I know that its first copy will arrive at r sub I. When will its second copy arrive? Anyone? Based on the information I've given thus far, for the task tau I, the first copy arrives at Ri, and if I know Ri, then when is the second copy going to arrive? A 1? We have only.
Is it 2 tau I?
Say it again.
Is it twice tau?
Well, tau is not. Tau is just the name of the task, right? So I think you mean t, but
T, yeah.
no, it won't be twice ti. It will be ri plus ti, right? Because if the first copy arrived at ri, next copy will arrive at ri plus ti. The one after that will be ri plus 2ti and all, right? So the if I call the first instance to be instance 1, then instance k will arrive at ri plus k minus 1 times ti, right? So this is a time series, which is a series of tasks which starts at for the ith task, its first copy came at ri after the system booted up, and then the next one will come ti later, and next one another ti later, and all so on and so forth. And likewise for jth, it will be rj plus tj, rj plus 2tj, and so on and so forth. The bigger point I'm wanting to make out here is, if I know both, I know the t sub i's for the different tasks, and if I also knew r sub i's, for r's for all the tasks, then everything about my system would be known, the entire future, right? When every task, every copy of every task when it is arriving, right? There's nothing unknown about the system at that point. And for those systems, I may have a computationally complicated problem, but I can solve everything. I can unroll the time for ad infinitum and give you a schedule. I can just work it out. So, but that's not how real systems are, because some of these tasks are a result of some external world interaction. So while tasks may be periodic, their first copy when they arrive depends upon which run of the system it is. It could be that in one run, the first copy of task 1 comes right after I booted up. In another run, maybe arrives a little bit later, and they may arrive in different orders. So every run, every time I reboot the system, if I were to examine when the tasks arrived, they look different because the first copy is different. The phases are different. That's the main point. So there are, computationally, you can say I have two different problems out here. One version of the problem is where I know what the R values are, and therefore everything about the system is known right at design time, and I can solve that problem. I can figure out when to run what. It's what you would call as a static design problem, right? Everything is known upfront. And the other version, so people refer to it as concrete. Okay, I'm giving you a concrete instance of the problem. Everything about timing, how the future looks, is known, and again, it may be computationally a challenging problem, but at least in principle, you can at design time say, you can develop a schedule at design time, right? You can say, I'm going to run this copy of the task on this processor at this time. You can work everything out. The more general problem is, every time I boot up the system, something different is happening, and that is the non-concrete case. And in this particular case, my OS has to figure out things, because every time the OS runs, it's facing a different situation. So just something to keep in mind, and we'll be focusing on the latter one, because that's kind of realistically what happens. Third thing, tasks have runtimes, right? Every time a task comes, an instance of a task comes, that instance is going to need some CPU time to run, CPU, GPU, whatever, right? Some time to run. And we call that to be C1, C2 through Cn. So task tau 1 needs time C1. Task tau 2, every copy of task tau 2 needs time C2. Every copy of task tau n needs time Cn. Now again, we have made a lot of assumptions out here which don't hold in practice. In practice, every time you run a task, its time may differ for a variety of reasons. It's computation, actual computation time, how many instruction, how much time it needs the CPU for. So one thing is that input values may differ, right? I mean, so oftentimes our algorithms take different time depending upon different inputs. There may be cache related effects, right? I mean, depending upon what was in the cache or not, different instances may take different amount of time. Then it could also be that the CPU frequency has changed because of power management or thermal reasons. So again, computation time may change as a result. So in reality, the computation time, the time that clock a particular task will take varies considerably. So one approach, there are a couple of ways you can seek to deal with. One is you will say, it varies a lot, and so I'm going to have my operating system make use of that. The challenge you face is you don't know beforehand how much time a job is going to take, right? It's kind of like I'm a service provider, a new job comes to me. How do I know how much time this job is going to take? So usually we design systems based upon our prior experience, on an average how much a job takes, and then we hire that many service providers or provision that many CPUs so that we can keep up with the load. But then sometimes our estimates are wrong. We may have idle workers or we may have shortage of workers. And in computing parlance, if I have excess workers and that's sunk money, right? CPU sitting idle, I can certainly save some power by idling them, but I've already purchased them, so that they're still there. And likewise, if I have a shortage, then I can bump up the CPU speed and all. So I could do those games. For our purposes, for scheduling purposes, one of the things that we do is we say we're going to go with the worst case. So the C1 through Cn refer to, if you see worst case execution time, how much in the worst case, accounting for data values and cache effects and all, what does this task take? Now, you may say, this sounds like we're making a big deal out of very little stuff, but actually if you look at even for common signal processing type routines and all, where you would not let's take JPEG, right? Compressing an image or decompressing an image, you imagine, I mean, doesn't sound like it should vary much, right? But actually it varies a lot. So if you a lot of these common algorithms essentially show a dynamic range of like as much as factor of 50 to 100 between the best case and the worst case because of data dependence. Deep down, a lot of these things have iterations and things like that, which kind of affect the computation time. So C1 through Cn are worst case execution time, and actually there is a whole body of literature even now on estimating what the worst case execution time is for a particular piece of code. That's not an easy problem. Some of you may have heard of in computing a problem called halting problem. Anyone knows what that is? What does in computing the halting problem refers to? Okay, I'll very briefly, it basically says that I give you a program and I ask you a very simple question. Will this program halt in a finite time? And I'll let you Google and find out what the answer is. Point is, these problems are hard problems, okay, or in some cases impossible problems. So finding what's the worst case execution time of a piece of code is not easy. So we are hand waving that away. Usually the approach is you're going to profile it, you're going to run this thing under a variety of circumstances on a variety of inputs, and then we're going to say I'm going to look at the distribution and based upon that come up with this. So that's the runtime. Relative deadline, D1 through Dn. This basically says after a copy of a task arrives, when do I need the result? right? So let's say I had those sensor measurements arriving every 1 second. Every time a sensor measurement comes, when do I need the result by? What do you think, what factors do you think will affect this requirement? And let's take a very simple thing. There's a camera, let's say a Zoom session, okay? There is a camera looking at my face, is collecting data, collecting a new frame every 30 milliseconds, let's say. And now I have a system, and let's imagine the system is, on the other side is you. So that image is being displayed to you at 30 frames a second again. To this system, I have to tell something about the deadline, right? For frame number, a particular frame, right? Let's say frame number 100. From the moment that frame became available, the camera produced it, to the point where the system has to finish processing and sending and whatever and display to you, right? So that's the delay, and let's call it D. What do you think affects D in my example? Like where would that come from, that requirement on D? Anyone wants to take a shot at it? There's nothing tricky out here. Just think about the problem a little bit.
The deadline for the image, right?
Deadline for the task, right? I'm telling, what will I tell the OS? Yeah, right. The system which is taking the camera images, which are arriving every 30 millisecond. What deadline should I give to the OS? What factors would affect the deadline that I will give to the?
I want it to sync up with the audio that's coming, right? So that's one factor.
Why would that affect the delay?
Why would that? What? Sorry.
Why would that affect the delay that you would tell?
Oh, you would set a constraint so that like the picture and the audio aren't
but
super out of sync.
True, but that's not what I'm asking, right? I'm asking, let's say there's no audio. So again, let's say we are doing an audioless Zoom, right? Let's hypothetically. So, what all factors would affect the delay requirement?
Connection.
Okay. Anyone else want to take a stab? There's nothing tricky out here. This is just there are quite a few of you on the class, so anyone? There's nothing, like I said, nothing tricky. It's not even related to what is on the slide. I'm just asking, let's say I gave you an operating system to which you can now say this is the delay. So what all factors what will lead you to decide on a number for the delay in this example? Okay, can I give a delay of 1,000,000 years? Doesn't make sense, right? So what factors would affect that? I'm going to do a liveness test out here. Nitin, what do you think? I want to see how many of you are not even there. Okay, you are there. Okay. So, liveness is a great property in computing. Okay, so Nitin, yeah.
Maybe I just think the limit to the delay cycle, and maybe also the clock at which the processor is running.
No. Why does it depend on any of those things? Why would it depend on clock that the system? All we are saying is that the system says, I'm happy to process this task, every instance of the task. Just tell me how much delay you give to me. Right? That's all that's happening. This D is basically a contract that's going to happen, right? So why would it depend on clock and stuff like that? All the system is, you tell me. So can I, in my example of Zoom, would I give a million year? Well, if I give a million year, then that frame would potentially take a million year to process and come to you a million year later, and of course that doesn't make sense, right? So does that suggest to you something, that some factor that affects the delay? Is delay?
I'm just able to think about the maximum time that it can run for to not occupy the whole processor.
No. So again, goes back to the discussion we were having earlier. Think about this. Is this requirement, is it a property of the system or the environment? Is it an expectation? Is it a requirement? What would affect this thing? Let's say if so again, if we are engaged in this bidirectional thing, let's replace image by sound for a moment, right? Would we be able to engage in this bidirectional back and forth if the delay was too large? We wouldn't be able to, right? I mean, so from applications alone, there would be, from perceptual reasons in human applications, or if it was that Patriot missile thing, the missile is coming in and I have to shoot it down, right? I mean, these delay requirements come from application perspective primarily, right? I mean, so an application would dictate how much delay is acceptable for the needs of that application. It has nothing to do with what the system can do or cannot do, right? I mean, yes, it may turn out that the system may say, hey, your delay requirement is too tight, I can't meet it. Or yay, it's great, you are giving me a pretty doable delay requirement, and I can meet your delay requirement and I can also sleep. Okay, so it depends on, that's a system's call. But D is just fundamentally an application requirement, right? That dictates it. So in a lot of our things, like let's take the image one. If I'm on a one-way thing, if you are YouTube displaying movie at people's homes, then the delay requirements are a lot more relaxed because there's nothing more bidirectional, but not fully, right? I mean, when I'm playing YouTube movie and if I press the pause button, and if the pause button is not handled locally but goes all the way back to the server, then there might be issues there that there is a lot of video still in the pipeline. So sometimes there might be other things, but in general, perceptual requirements. So when humans talk to each other, if you have delays of more than, let's say, of the order of 100 milliseconds or so, then bidirectional communication becomes not possible. Okay, it becomes pretty annoying. So these kind of latency requirements come from the physics of the environment, what is acceptable or not. But additionally, then there is once you have this, then you may have a system level constraint. Now, one other thing which happens often is that human world operates at a much slower rate, right? I mean, I just said 100 milliseconds. So, oftentimes you are designing systems when you don't know what that end-to-end delay requirement is. So oftentimes people, particularly in electrical engineering, we take a lazier way out. Okay, and the lazier way out is that we basically say, as long I'll set the deadline to be the time period. All we say is finish this task before the next task arrives. That's all it says, right? I mean, if I say di equal to ti, then it's saying that for the ith task, from the moment a copy of that task arrives, you have to finish processing that before the next copy arrives, right? The deadline is equal to the period. And there is no rational reason to state that other than kind of basically saying that, if I have a single processor and if deadline is more than the period, then it's possible that then that doesn't make sense, right? So deadline has to be no more than the period if there is a single processor. If there are multiple processors, right, multiple cores, then there is no rational reason for di equal to ti, and di equal to ti may actually not be acceptable. So in our camera example, if my camera frames are coming every 30 milliseconds, then if I give di equal to ti, then that means that we are telling, hey, you can take up to 30 milliseconds to process this frame. Well, if I'm consuming 30 milliseconds and then let's say there is also some delay in the network and some processing at the far end, maybe I will not meet my perceptual requirements of 100 milliseconds. And we often face these problems, which is that an upstream system may eat up a lot of the end-to-end delay budget that you may have. So in complicated systems, one of the tasks that you have is, from application perspective, what the end-to-end delay needs are, right? From the point data is produced to an action is taken, what the overall delay is. But then I need to tell one subcomponent, one node in my system, how much delay it can have. So like, let's say I'm talking to you on my smartphone. I have at least 3 components: my smartphone, the cellular network, and your smartphone. And one question which comes up is that how do I divide up the delay? And that's often not very easy. And this is where these are simplifying assumptions like deadline equal to period don't necessarily work out. Anyway, that's a long story. Point really I want to make out here is deadline has nothing to do with the system characteristic. It really is an application requirement, and one has to keep in mind. And then the reason it becomes a system characteristic is that there may be things that the way you have split things, right? I mean, end-to-end delay gets split into a particular nodes requirements and all. That is where you may have some additional constraints coming in. Other requirements, it's very common to assume that these tasks are fully preemptible. That is, operating system can stop them at any moment and restart them from where it left off. So do you think that's true for every task? Like, can you think of tasks where it is not easy to stop and restart? Computing in general, if you look at just normal computing, yes, I can context switch between 2 instructions, right? I can after an instruction I can save the program counter and the stack and then restart at a later thing. But can any of you think of tasks that our systems do where I cannot stop in the middle? Anyone?
Transmission.
Yeah, transmission of a packet. If I stop transmitting a packet in the middle, then I really have to discard whatever I have transmitted and restart from the beginning. Okay, and part of it has to do with a packet transmission. We do some synchronization at the beginning by sending a packet header and preamble. So packet transmission is something that is not preemptive. So if my in some pretty if my radio is not a separate processor with a separate device with its own processor, if my main processor is feeding byte by byte as the packet is going out, then I can't just stop in the middle. It has to go in one chunk. Okay, so this preemption assumption one may encounter often, that there are things that may not be preemptible because I'm taking a sequence of actions which I have to do atomically. Once I started, I have to sort of go through it. So preemption assumption. If you have one strategy is, if I need things which are non-preemptible, it's best to have them be handled by a dedicated processor or a dedicated hardware. Okay, and then finally another assumption is that OS overheads are zero. Okay, essentially what we are saying is, when we save the state of a computation, when we resume it, we are just going to assume that these things take very little time or relative to rest of the times. Okay, of course they take some time. So when you look at data sheets of operating systems, they will often advertise these things. They will say context switching overhead is so many microseconds or something like that, and so that will give you a sense of how agile they are. Of course, a lot of these things depend on the platform you are running on. So let me ask you another question. Which one of these different variables that we have seen, T, R, C, D, depends upon the speed of the CPU? That is, if I were to give you one descriptive system and then same application running on a different CPU, which one of these things will change? T, R, C, and D?
C. Maybe C.
C, yeah. Do you think
C, yeah.
Okay, I'm suddenly getting a lot of echo, but yeah, C. C is one. Anything else?
Maybe the deadlines as well.
Deadline. Okay, so why would deadline depend upon the processor or CPU? What would be the reason? C is obvious, right? It's computation time, so of course depends on the CPU. Why do you think deadline will depend on the CPU?
I just thought that if everything were to execute faster, then its restraints would be different because the timing of all its computations are different as well.
No, it won't. Now, there is a little caveat, which is it can depend upon the speed of some other CPU. Let me explain. Let's say there was a pipeline of 2 CPUs. I have an overall deadline of 1 second. So CPU 1 plus CPU 2 together should do 1 second. But if CPU, we can start out by, so if CPU 1 takes 0.25 second, then CPU 2 will have 0.75 second budget left. Barring those situations, if I think of my system as single system, then it's really a function of application, which was a point I was making earlier, which is how much delay is acceptable is really the function of application. And in general, sort of human perception and all tends to be in tens to, let's say, a few tenths of milliseconds. So a lot of delay requirements tend to be at that level. In other kind of control systems, let's say you're designing something for avionics control on a supersonic fighter pilot, things might be very different. If you are CERN and designing something for atomic particle activity, you might be dealing with nanoseconds, right? I mean, it's really a function of application. So no, it's not dependent upon the platform at all. One other thing I would also mention while we are on it is open loop applications which have no feedback, right? One party sending something to the other. As such, there is no computation delay requirement in it. For computation later, think about it, right? I mean, if I collect some data and send to a party and there is no feedback ever from that party, right? There is nothing that party does which affects me in any shape or form, directly, indirectly. then I can have infinite latency and I'm still okay. It would be equivalent to an alien on Alpha Centauri sending me a message, or an alien on Moon sending me a message. Who cares in that case if it's just one direction, right? I mean, the only way it makes a difference is when there is an action involved. That if I am now going to do some action, and that's when the delay matters. So in settings where there is a control loop or there is a bidirectional engagement, that's when D matters. But D is a requirement on the CPU. D is not affected by CPU, right? The CPU and the OS have to meet D. They don't dictate D. Okay, so I'm going to let's see. Really wish Zoom had a better interface for single screens. Okay, so last slide for today. So scheduling algorithm. So given that framework, the scheduling algorithm basically boils down to when should I run a task on the CPU, or if I have multiple CPUs, when should I run which task on which CPU. And if my CPUs have changeable frequency or changeable frequency and voltage, then it's when should I run which task on which CPU with what voltage and what frequency, right? That's basically the scheduling problem. Now, in situations where R was known, right? R was known at system design time, then everything about the system is known. When is a task coming in, when is it needed by, everything is known, and I could solve that problem at compile time, right, when designing the system. But if R is not known, then every time the system runs, it looks different, right? The events are coming potentially in a different sequence, and I have to now do some runtime actions behind it. So so one very common strategy for scheduling is what is referred to as preemptive priority-driven scheduling. So this strategy does the following. What we do is we give to all the tasks something called a priority. This priority, you think of it as a number, and so larger the number, higher the priority, let's say, or what depends, like they're ordered in some way. And this priority given to a task can be static, that is at compile time I decide forever that sensing task has highest priority and radio task has the lowest priority. I can decide that ordering up front and keep it fixed, or I can do it dynamically at runtime on some basis. Okay, so relative priorities of tasks may change depending upon some algorithm that I have. But the scheduling algorithm is super simple. All the OS will do is it will say at any instant the highest priority task is the one which is going to run. So if you recall, I had in the previous lecture I had that diagram. Let me pull it up. This diagram that I was referring to from previous lecture, where there was a ready state where the set of tasks which are ready to run reside, and then operating system have to decide which one of them should be actually running. Well, this algorithm that actually it seems like I have. So this algorithm that I'm suggesting basically says anytime I have to decide which task to actually run, I'm going to pick the task which has the highest priority. That priority could, as I said, could be static, that is we determine at runtime, or it could be dynamic. The OS is allowed to change it on some basis, and we'll see what those bases are that on Thursday. But that's the strategy. So basically, we have transformed the whole scheduling problem into a priority assignment problem. So as long as we have a sound strategy for giving priorities to tasks, then we'll show that you can meet deadlines. Okay, so all the deadlines and all kind of reduce down to how do we assign priorities, and in particular we'll see that how do we assign priorities statically, what will that achieve for us, and then going one step ahead and say, what if we were allowed to assign the priorities dynamically? Intuitively, you can think of like various ways of assigning priorities. I'll say more important tasks should get higher priority, or maybe tasks with lower deadline should get higher priority, or things like that, right? I mean, you can imagine different heuristic strategies, and we'll see which one of them lead to what kind of promise. They're just sort of one punchline going in. So this whole thing called rate monotonic and deadline monotonic, and there are various ways of doing these things emerged, and there continues to be kind of research, but kind of the area itself is reasonably, the early algorithms are reasonably old. Essentially, there is a good solid understanding at this point for single processor type cases. You can design these things in a manner where you can make promises. That's the main point. But the multi-processor case is very hard to make any promises about. So that's kind of the state of the art. So we are going to talk about that next time, other than to say that Mbed OS and most operating systems which claim to provide real-time support essentially provide some way of assigning priorities to threads, and then all the operating system does is it makes sure that at any given point in time it strives to run that thread which has the highest priority. Okay, so I'm going to stop at this point.